Hello, everyone. I am Fei Xiao, a data scientist in Shopee, Singapore, and I'm also a PhD candidate in National University of Singapore from Prof. Ben Ching Wei's group. I will present our fraud detection framework, MINT, detecting fraudulent behaviors from time series relational data. For my presentation, I will firstly give you some background about fraud behaviors in e-commerce platforms. Then I will briefly present existing fraud detection works and give you a detailed explanation on how does the proposed fraud detection framework work. I will also show some experimental results to show the efficiency and the effectiveness of MINT. Then I will give you a conclusion about our work. Firstly, fraudulent behaviors are ubiquitous. A variety of e-commerce fraud have become threats to the platforms and the business users. Those fraudsters or cybercriminals may use a stolen credit card to purchase or take over some others' accounts. This will cause direct loss to those normal users. There are also some other users who profit by helping certain merchants with brushing orders or posting fake reviews about some other's business. These actions will also have a significant negative influence on the healthy development of e-commerce platforms. By comparing the behavior patterns of the fraudsters and the normal users, we found that we can detect the fraud behaviors based on users' daily activities. For example, the user A is a normal user and the user B is the fraud user. A normal user usually compares different items and their reviews before they make a purchase. By comparison, a user engaged in brushing fraud may directly search the targeted product without making any comparisons with other items. By learning the intentions of the user's daily activities, we can easily distinguish the fraud and the normal behaviors. But some fraud users may pretend to be a normal user by performing the similar actions. Therefore, to enhance our ability to identify fraudulent users, we need to extract more profound behavioral traits from their data. In recent years, many efforts have been dedicated to fraud detection. For instance, in the first paper, an attention-based model was employed to understand payment-related actions for chargeback fraud detection. And the second paper utilized users' daily actions, implementing a tree structure to reorganize the sequential actions and then leverage LSTM to capture diverse intentions. Additionally, certain works are involved the creation of a comprehensive heterogeneous graph for transaction events, interconnecting transaction-related entities of users. These works have achieved quite good fraud detection results, but the exploration of users' behavior data is still insufficient, resulting in many valuable behavioral features not being effectively captured. For example, most of the works do not use temporal information. Some works use the timestamp information only embed them to some features. I think these are not enough to capture users' time-related behavior pattern. Well, by analyzing millions of users' behavior sequences, we found that both the short-term and the long-term intentions of the user will be important to the fraud detection task. For example, In a account takeover fraud scenario, a fraud user tend to quickly change the passwords of the account and update some personal details. Well, the fraud users may take several days to test whether it is safe or not to make purchase using this account. Therefore, to fully capture users' intentions, we should be able to learn the behavior pattern in both the short-term and the long-term views. If we treat a behavior sequence as a graph, the action nodes that are within the same session can be directly connected, and they can form a short-term intention. Then multiple short-term intentions can be merged together as a long-term intentions. By representing each user's behavior sequence as a graph, we can formulate the fraud detection problem as a binary graph classification task. In each behavior graph, the user's actions are represented by the corresponding nodes, and the action attributes are the node features. We create 3 different graph convolutional matrices for each behavior graph, which represent 3 different views for the graph. Here is the equation we use to calculate the normalized edge weight between 2 action nodes. If the time interval between 2 nodes are very small, they usually have very strong connections. By setting the value of rho to close to be 1, each action node will be connected to many other nodes, which can be aggregated to learn the user's long-term intentions. The receptive fields of the behavior graphs are designed to grow exponentially. For example, for Shopee dataset, we set the value of rho for the first layer to the third layer to be 0.6, 0.6, 0.9, 0.9999. In the first graph convolutional layer, by aggregating neighboring action node features to a targeted node, it will capture users' short-term intentions. And then multiple short-term intentions can be aggregated to learn the mid-term intentions. It should be noted that we cannot use a single graph convolutional matrix for all the layers. Because a behavior graph is divided into several unconnected graphs, unconnected subgraphs, and the node information among different subgraphs will not be communicated, even if the depth of the graph convolutional layer is very large. The most efficient way is to assign different values to rho. But if we apply a vanilla multi-view graph convolution model to each behavior graph, users' fraudulent behaviors may be smoothed by its normal ones. For example, all users have a lot of visiting homepage or searching actions. Their embeddings may dominate the user's final representations. To address this issue, we design a simple but efficient gated neighbor interaction unit to calibrate the information passed to the targeted nodes in each graph convolutional layer. In that case, most of the information contained by those very common action nodes, like the visiting homepage, will be filtered out when doing the feature aggregation. So why the proposed MeetGC method can achieve more effective performance than existing method? Firstly, we know that the feature aggregation and the feature transformation in a GNN can be separated without degrading the effectiveness. By setting the value of rho to be 0.9 or 0.9999, the graph convolution layer can function as a deep graph neural network. Compared to those deep GNNs, which achieve larger receptive fields by employing more graph convolutional layers, we only need 3 graph convolutional layers. In addition, as the action node is not information dense, the time-aware edge weights are much more effective than the attention-based methods. We firstly tested the proposed meet on our Shopee dataset. Shopee C1 and Shopee C2 are 2 different regions in Southeast Asia. We also verify our framework on Amazon public dataset. This figure shows the average degrees of the action nodes in different graph convolution layers for 3 real-world datasets. It can be seen that the receptive field of 3 layers expands progressively. In this case, last graph convolution layer can cover a long time range and learn the user's long-term intentions. The metrics we used to evaluate the performance of Mint in fraud detection tasks are AUROC and the recall at precision equals to 0.9. We compare our work against 5 sequence-based models and 5 graph-based models. The sequence-based models treat each user's time-stepped activities as a sequence, and then utilize the behavior sequence information to predict the fraud level of each user. For the graph-based method, like GCN, GAT, and GCN2, we build a behavior graph for each user with the value of rho equals to 0.6, which is the same as the first layer in our Mint. And we also reset all of their edge weight to be 1. And we also conduct aberration test by removing the multi-view function and the row interactive scheme. And by comparing the performance of the Mint with its 2 aberration tests, we found that both of the methods are very useful in our proposed framework. The performance of Mint in terms of AUC are presented. Then let's see the function of the row interactive scheme in mitigating the over smoothing. From this subfigure, we can see that for most of the adjacent, for any 2 adjacent action nodes, their features are quite different. But for this subfigure, we can see that most of the action nodes will have the almost the same features in all of the dimension. So it means that the proposed row interactive method will have to avoid the oversmoothing issue. And for the multi-view graph convolution, its main advantage lies in that we need much fewer layers to capture multi-hop neighboring information. And since we do not use a attention scheme to calibrate, since we do not need to use an attention scheme to calibrate the aggregated information, we can perform faster than most of the important baselines. So because the short-term view and the short-term view and the mid-term view of the behavior graph are very sparse, we can employ sparse graph convolution, in which the computational complexity is determined by the number of edges. Therefore, Mint can easily scale up to longer user behavior sequence. It can be seen that the performance of Mint is in the large data is still much better than the baselines, and the training time is almost linear to the behavior sequence runs. By the way, in the readout layer of Mint GCN, we design an attention-based feature extractor to learn the weights of each action node. In this case, we offer global and local interpretation for the model prediction. We also create a new metric called normalized reciprocal rank at K to evaluate the importance of each action type to fraud behavior detection. And from this result, we can find that the most suspicious actions are something about the refund or login with password. These actions are related to the refund fraud and the account takeover fraud. Okay, in this work, we redefine a user behavior as a time-aware behavior graph. We build 3 different graph views to capture the user's intentions from various perspectives. And our approach involving learning user intentions by considering both the temporal patterns and the activities that engage in on the e-commerce platform. We devise efficient and potent approaches for learning behavior graphs, addressing prevalent issues in existing GN models, including the over-smoothing and the receptive field expansion. Okay, that's all for my presentation. Thank you for listening.